So let me try to I think now it's look okay. Uh, okay, so let's start again. I'm sorry for the interruption. Now you can see my screen here.
Yes.
Yeah. Okay. Uh, I think the problem is still happening. Maybe we somehow connect each other. I think we somehow connect each other. I don't know. Okay. Anyway, but I can manage. When I make the full screen, it's a bit strange. No, no. Let's try to work it out.
I think we could see your slides.
Yeah, but I cannot really move anything.
Oh, because I saw them moving, like moving
Yeah.
from one
Okay.
slide to
Okay.
another.
Yeah. Okay. Thank you. But I will not make full screen, and I will go like this. So but you can still see my screen. So okay. Right. Okay. So let's talk about the transition state optimizations. Locating a minimum you have done yesterday is relatively easy. You can start from a given structure, and you can use any optimization algorithm that you can use to minimize the transition state. But if you think about you can easily optimize a local minimum, but transition states are challenging to optimize. It's because we don't have a standard algorithm to do that. There are several algorithms I shown here. You can share. It's okay.
Yes, but I don't want to recreate.
No, it's okay. It's okay. It's okay, Julie. Now I'm not making full screen, so you can stay. It's okay. Okay. Right. Okay. So yeah. So these are some methods in different computational codes, and you can use any of these algorithms to run transition state optimizations. Just to remind you, yesterday you located local minimum, shown here, for example. The transition state is a first order saddle point. The shape is like this. You can see it connects to two local minima in this side, and it's of course a minimum in the perpendicular direction. So the shape is like this. Now if we go into the tutorial, we can it's in our workshop website, and you can go into the tutorial 2 reactivity, and if you click here, you will go to the transition state computation. So we are going to use NEB calculations. NEB is a method to find transition states. Okay. Now, to run an NEB calculation, we want to generate approximate structure of your reactant and the approximate structure of your product. So here is the product's reactant structure. It has our starting molecule with the water, and then here is our product structure. Now, you can find the starting structures for your calculation here. So here structures, you have the reactant. Here you have the product structure. You can simply take the coordinates from here. Now the input file, I want to tell you a little bit about the input file. Input file is something like this. Your first step would be to optimize the reactant complex here. If you can optimize, you can get a better structure, but you can of course use the current structure, it doesn't matter. I want to explain the keywords. You're using that method, PBEH3Z. The meaning of that also explained in the tutorial. We are using PBE functional, and it has non-local hydrophobic exchange 42%. It's kind of mixing between the conventional PBE with the hydrophobic exchange, so some functionals have that option. And the basis set by default when you put this keyword is def2m SVP. So when you put that keyword in the input file, it will use PBE and 42% hydrophobic exchange functional, and also the basis set will be def2m SVP. Now, to optimize the structure, we want you can of course optimize the reactant complex and the product complex, which is fine, but let's don't worry about it. We directly use the given structure to run the B calculation. Right, okay, so right, okay, so I'm going to create a new directory in my computer. So now we want the input keywords, which you can find in the the tutorial web. Here the idea is follows. Here we are running PBEH minus 3C density functional, and the triple zeta basis set, NAB optimization, transition state optimization, followed by a frequency calculation. For the NAB calculation, we give the reactant and product structures. So we must give the reactant and product structures in the input file, and in the same directory we must place the product and reactant structures. So we have the input structure. So now let's create the reactant input file. We have the coordinates in the this is our reactant coordinates, so we can use that. Here. And then the product structure. So this is our product and this is our reactant. Right, okay, so now in the here is our input file, and in the same directory we have two extra files. One is the product, approximate product structure, and then you have approximate reactant structure. So all two structures must be given, and then these two structures will be used at during the calculation and try to connect the reaction paths between the reactant and the product. So the keywords are okay. Now we can run the calculation. Right, okay, so the calculation is running now. So this calculation will take a while actually. If you run this calculation, maybe it will take half an hour, or it may be 1 hour, 2 hours, depending on your computer speed. Anyway, let's don't worry about it, so allow it to go. And I have done this calculation yesterday, and then I will go through the outcome. Right, okay, now you can see here So after the computation, you can NAB calculation, you can see many output files, and then you can find some interesting information in these output files. First of all, let's look at the output file, which is test out, and in this file you will see normal termination after the computation, and if you go up you will find information about vibrations, so it's important to look at it. And let's look at the vibrations. So here is the vibration. Now you can see one imaginary frequency. Okay, so it means that you got this transition state. So the structure approach to a transition state, or a first order saddle point. That's why it has an imaginary frequency. Okay, let's look at the XYZ file, as you know, generates the final structure, which is the transition state structure in this case. You can open that structure using Avogadro software, and you will see the transition state. So in here you can see that atom is moving from one oxygen to the other oxygen. Let's check whether we can look at the frequencies. So I'm just looking at the vibrational frequencies, and you can see the imaginary frequency here. And it's very important you look at the motion of this imaginary frequency corresponding, well, vibrations corresponding to the imaginary frequency, and you can clearly see that atom is moving from one oxygen to the other oxygen. So that's very nice. So that's exactly what we really want to see. So during the reaction, that's what we expect. That's very nice. Now and now you can look at the in the output file you can find path, I mean NAB outcome. We can check it. So you can find the path summary, and then there are some I accidentally edited it some way. Anyway, okay. Now, in the path summary, you can see the energy of the data points that it computes, and it can also give the energy of the transition state here. So if you plot this, simply take these energy values, and you can use simply Excel and try to plot these energy points. And then you can find how energy changes with the number of steps. Now you can see plot like this. So you can see according to this calculation, point number 7 is the transition state, which is basically 1, 2, 3, 4, 5. 6. This is the transition state structure. So you would see transition state structure over here, and you can see it connects to the reactant side, to the product size. So you will always see a nice reaction path using NAB transition state optimization. So always look at this. So now we confirm we have a transition state, and then what would be the next step? Right, okay, so we have a transition state. Make sure that you have one imaginary frequency, which is very important, and always look at the vibrational modes corresponds to this imaginary frequency, and then it will show you what's really happening during the vibration. So it will give an idea about the nature of your transition state. Okay, so what is the next? The next step is to perform IRC calculation, which is intrinsic reaction coordinate computation. This is very standard, and after getting the transition state, you can use that transition state to perform the IRC calculation. So in IRC, what's happening is basically you have a transition state like this. Sorry. You have a transition state like this. And what we do is basically we start from the transition state structure, and then you follow the minimum energy path towards the reactant and find out the approximate reactant. And you also work towards the product side, and you can find the product structure. Okay, so finding the IRC path is very important because it connects the minimum energy pathway to the reactant and to the product starting from the transition state structure. This is very important because in that way we confirm the connectivity between the right reactant and the right product to this transition state. Okay, so imagine you are on the top of a mountain, and then if you try to go downhill, you can go into many different directions, right? But our idea is to go to the most energetically lowest pathway towards the reactant or the product. So okay, to do that, in the tutorial you can see IRC, intrinsic reaction coordinate calculation. So it has an example. Of course you can try it, but I am going to focus on our computed transition state and then use that as a starting point to compute. So we get, this is our NEB calculation, and we located the transition state. So I'm going to use that transition state to begin the IRC calculation. I can share my input file with you. So I will share the input file. Oh. I cannot send messages. So it says it's too big, so I will place it in Slack so it's easier. So you can look into the Slack. So in the input file for the IRC calculation, we are using the same method. The extra keyword is the IRC keyword, and here we ask calculations to follow maximum 30 steps. I mean the iterations will be maximum 30. And this is our transition state structure. So you can simply submit this job, and so this calculation will also take maybe half an hour or 1 hour depending on your computer speed. So it also generates many output files, and I will tell you the most important information. Let's look at the IRC output. I have done this calculation yesterday, so you can see some important information. So it's a normal termination, and if you go up, you can see here the IRC path summary. So you can see our transition state structure is here. This is the energy of the transition state, and then it looked into the reactant side. it follows 30 steps, because in the input file, if you remember, we ask computation to follow 30 steps here. So you can increase this number. If you increase this number, it will work further. Okay. And for the product side, it's also goes, it went for 30 steps. And let's try to plot this energy and see what it looks like. So if you plot the energy versus the number of steps, you will see a plot like this. Yeah. So this is very nice. You see, starting from our transition state structure, we went to the reactant side, 30 steps, and the product side, 30 steps. So in this way, we know if we follow the lowest energy pathway, we end up here. If we follow the lowest energy pathway for the forward side, we end up here. So we know the approximate reactant species here, and approximate product species here. Now, in here, the tutorial uses a different example, but the idea is essentially the same. And you can try this as well. Okay. And then you can find the approximate reactants and approximate product starting from the transition state. So in the output file, you can find different in the directory of your computation. You can find many different files, and among them you can find this IRC _f xyz files. They are interesting because these files have very useful information. So let's look at it. This is the IRC calculation. Here you can see different XYZ files, and what is important here is that one, IRC full trajectory. Maybe let's try to open it. Full trajectory. So here is it. This is the file we want to look at. If you open this in Avogadro, so you can see it has why I just want to stop the animation. So okay, now it's better. Here you can see 61 frames, and then you can see if you run this, you can see the full IRC path, what's really happening during the IRC. So this is our reactant side, and if you play it, you can see how what a molecule approaches to this molecule and reacts. So this is very beautiful. Okay, now in here, this is our reactant side of the minimum energy path, and this is the product side. So the next step is to choose this structure and compute the optimize the reactant and the product structures. So so you can save this as reactant. So I cannot save this as a XYZ file. Anyway, it's okay. Well, you can do it like this. Here we have the reactant structure. So we can take this reactant structure and then we can simply set up an optimization because in the IRC path we have that is approximate reactant structure. So we must start from that point and minimize the structure, and then it will further relax and go to the reactant. You should do the same here. Okay, now let's try to do that. Now we want to optimize it and run frequency. So this is our reactant optimization, and then we start from our product structure here, which you can find in the trajectory file. Yes, the trajectory file. Where is it? Here is the full trajectory, and then we take the last point. So this is our reactant side, and then we get the product side, which is the last structure, and then we optimize the structure. Right, okay, so it will take a few minutes to optimize the reactant and the product, and we will look into the data shortly. Meantime, I will give you time to ask questions if you have. I can see some questions in the so this is a very good question. Is it better to increase the number of steps for IRC to the end to the product reactant, or choose a smaller number of steps and then optimize each? Okay, so it's better if you can increase the number of steps in your IRC calculation. In that way, you can obviously go further. So you can here you can see the energies not really came into a minimum, right? So if you follow another maybe 30 steps, you may approach to the reactant side. The same here. So we are quite near to the product, but maybe it's better to go further. So you can simply increase the number of steps in the IRC computation. So if you this number, okay, so if you increase this number to 50, maybe you go further. So at the same time, you should remember it is going to increase your computational time. Okay, if you are working with a very large molecular system, going for 50 points may be harder. Okay. The question, I'm unable to attend the live sessions. Yeah, we will share the videos later. Okay, don't worry. So you can. It could just, okay, so what is that? IRC calculation so shows similar energy for the reactor. Yeah, okay. Yeah, so you can see the answers here. Yeah, that's true. Some reactions can be endothermic, some reactions can be exothermic. We will figure it out after the computation. Okay, question: when defining the reactant and the product, do we have to pay attention to the initial distance of the molecule? Example, if I put, okay, yeah, this is a very important question. So it's okay, so it's better to give you a realistic starting point and a realistic endpoint. For example, let's look at this IRC path. For example, if we want to locate this transition state, let's go back to our transition state. Okay, so ideally you would give a structure near to the transition state. So if you give a structure here, this somewhere here or somewhere here, the computer can find the transition state quickly. So if you give a structure here and a structure there, so it's the distances between the reactant and the product are quite far. I think the structures are quite different, and then finding the transition state may be time consuming. So it's better to give a realistic starting point. It should not be perfect, but approximate and realistic reactant and realistic and approximate product. So that would be enough. You don't need to make the structures quite far away, and if you do that, the computing time may be very slow, and maybe you will not find the transition state. It may not converge.
Hi.
Yeah.
Sorry if I jump in. I just
Yeah.
wanted to because it was I who asked that question,
Yeah.
because I would like to understand. So, if the long interactions are calculated within QM, or if everything is treated as local, so in the van der Waals radius range of action,
Mm.
because when we calculate electrostatics or van der Waals interaction, there is like a distance, like an atomic radii distance, and the electrostatic propagates further from that.
Yeah.
And so my question was, what if we place like the molecules a bit far apart? Will the program and QM in general treat like the long range, so that even if it takes more time, it will eventually come to the minimum of that? Or do we have to really put them close together so that the calculation can take effect?
Yeah. So that's a good point. Yeah. If you're using a method to treat long range interactions, you will be fine. But some methods may not really treat the long range interactions in a reasonable way. So then it's better not to keep them quite far away. So then you may not find the transition state. Your calculation may fail. So if it is relatively closer and near to the transition state, I think it's the perfect situation.
Question: when you say the method, are you talking about level of theory?
Yes.
Okay.
Yeah.
Okay. So there are
Yeah. Because
with diffusion basis set and stuff like that.
That's right. Yeah. So density functionals, some density functionals can treat the long range interactions, but some may be not good. So depending on the method you are using, and of course the basis set is very important. And if you use a large basis set, I think situation is much better. I mean, you can find the transition state even you have a relatively longer distance. So my recommendation from my experience is that you would give a realistic transition state structure. I mean, realistic reaction structure near to the transition state. So then the computation is easier, and you will find it relatively easily.
Because if you think in terms of molecular dynamics, like
Yeah.
all atom and force field,
Yeah.
when you like simulate proteins or lattice or materials or whatever, it's not given that you get like the most optimal configuration and the geometry, the initial geometry, because electrostatic are calculated very roughly in molecular dynamics, like
Yeah.
with a simple Coulomb coefficient
Yeah.
at equilibrium. So it's not like a big deal. But when it comes to QM, that's where the electrostatic effect comes into play.
Yeah.
And I was wondering, like, where is like the threshold between, say, I have a molecular dynamics, do I have like to, and I take a snapshot of it, and which I find like interesting from a geometrical perspective. This means that once I have that, I still have to optimize the geometry on QM level and then proceed to calculate the transition state, because I might not get the.
Yeah, that would be better.
Makes
Yeah,
sense.
if you have a protein system, of course, at molecular mechanics level, you cannot really find transition states, because the molecular mechanics cannot treat the bond breaking, bond forming, right? So you must define the quantum mechanical region and run this like a QMMM, for example. And of course, you should first optimize your snapshot and your reactant site, at least using QM. So, and then you will get a realistic structure to begin.
Last question, and I promise I'll shut up later.
No. You can ask as many questions as possible.
There was I sent a message, a question where I said,
Yeah.
well, shouldn't the product have like a lower energy? Because in theory, the lower the energy, the more spontaneous like the reaction could be. But somebody pointed out that what if you have like an endothermic reaction where you add energy to the system for like the reaction to happen? But I wonder, lower energy states and lower energy molecules shouldn't spontaneously react. So if I have something that is like at this height of my energy of my potential energy of my state, and then I have something that is up here, this should be favored in my mixture from a chemical standpoint. If I take like an infrared, I should see more of this product rather than this. This should still happen, like less spontaneously, but this should be like more abundant. So if I add energy to the system, eventually the transition happens. I add energy, and then how does this work? How can I predict if something is endothermic or exothermic?
So after computing the reaction path, potential energy surface, let me try to draw it. Okay, so here I can draw. So let's assume you get a situation like this. So you can see my drawing, I guess. So this is your transition state and this is the product. Okay, so now you can see the reactant side is relatively high in energy than the product. So this is an exothermic reaction, and this reaction has a barrier. So the reactant side, they have the vibrational levels like this, vibrational level, and then the reactant side, when it has thermal energy, it can vibrationally excite, and then when it meets the transition state region, it can move into the other side, and then it can relax through the vibrational level.
And in this case, the products are lower.
Yeah.
So they're more stable.
Yeah, yeah. So the forward reaction has a relatively low barrier than the backward reaction. So the forward reaction would be favorable, and reaction may be maybe not reversible. So if you go this side, you may not be able to come back depending on this height. So if you have enough thermal energy to climb the reverse, so it may come back, but the forward reaction is definitely favorable.
If you look at your Excel file of the exercise that we did, the shape of the curve is like a Gaussian almost.
Yes.
So there is, if you look at the lowest, the two minimum, like from the product and the reactant, it looks like the product on the right are a bit higher.
Yes. So that is an endothermic process.
So this indicates that it is endothermic.
Yes, it's like this, right?
Okay.
So and then so if you want to go forward, you must vibrationally excite and then meet the transition state and then go into the other side. Now in this case, you can see the backward reaction has a low barrier. So going forward is a little bit harder than going backward. So this reaction may be not favorable for the forward direction.
So my assumption was right, that I could find more reactant than products in my mix.
Yes. Yeah.
Okay.
Yeah.
But it's still possible to go on the right hand.
Yes. If you have enough thermal energy, you can go, but the backward reaction is favorable. So you can simply use Boltzmann distribution if you want to get the ratio between these two. I guess depending on the barrier, you can go if the barrier is lower, so it's a reversible process. All right.
Thank you.
Yeah, no problem. Let's check whether I have more questions. Is it format input file of TS that product should be written before the reactant should be written? Right. Okay. So the question is, I think he wants to know, he or she wants to know about the order of the file. Shouldn't the product up to the right? Okay. There are many questions about transition state computation. So I will ask this question: in the transition state calculation, where did you get the guess XYZ structure for? In this tutorial, you can find the guess transition state in the tutorial page. So if you go down, you can find the approximate reactant and the transition state structures here. Okay, but if you're working on a different reaction, you can create a realistic reactant and realistic product structure. You don't need to be perfect, but somewhat realistic structure for the reactant side and the product side, and then you can proceed the computation. What does the climbing image structure represent? So the energy is going up means you are approaching to the transition state. So if the energy is going down, so when you are approaching, when you go energetically higher, you are climbing up the potential energy surface and approaching to the transition state. Someone wants to know about the input file. In the NEB calculation, you can put the product here, reactant there, or you can also put the reactant here and product there. It doesn't matter. What we give is basically the 2 points, 2 data points in the potential energy surfaces. These are guess structures, and here you see you can also give a guess transition state structure. So this is also a nice approach. In that way, you give 3 data points, and then the NEB calculation may be faster because it has 3 data points. So you can also try this, giving approximate guess transition state. So then you have 3 structures in your directory: reactant XYZ file, product XYZ file, and guess transition state. And then you can you can begin the calculation with 3 data points. So this is also very useful. Let me check Slack if anyone wants to have a discussion there. Okay, I cannot see Anything in Slack? How can we generate the rate constant for the forward and backward reaction? Is it possible? Oka calculation. Rate constant. So I will be back to that rate constant issue later. So I have one of my colleagues, probably Bedmini, are you in the Zoom? And if you are there, can you answer this question? Rate constant, and you can write down the information. I will back to that question later. Right, okay, so now let's move to the next step. We have the IRC path. We computed it. And then starting from the reactant side and the product side, we optimize the reactant and the product. So now we have reactant structure optimized, product structure optimized, and transition state structure optimized. Then the next step is to get the reaction barrier. So how do we do that? I recommend you to look at this thermodynamics. So in the properties thermodynamic tutorial, well, it's a different tutorial, but you can also try this example, but let's use our present data to get the reaction barrier. So if you run the frequency calculation, as I told you yesterday, we use standard temperature and pressure in the frequency calculation, and you can of course change it if you want. And then if you do that, it will give you many different energy terms. So you can find the electronic energy, which is the potential energy of the molecular system, and you can also get the 0-point energy, which is also very good. And you can use 0-point energy in your total energy. Okay. And you can also get some thermal, vibrational, rotational, and translational energy corrections, and you can get the total thermal energy. Enthalpy can be computed using this equation, as you know, and the entropy of the system can be computed as well. Finally, Oka will compute Gibbs free energy using this equation, and Gibbs free energy is important because it has entropy in the total energy. You know, in some reaction, entropy of the reaction is very important. If you really use potential energy to generate the potential energy surface, it doesn't really count entropy. But if you plot Gibbs free energy, it counts the entropy, and then the reaction barrier may be more realistic. It has entropy effect into account. If you have a very bulky system, the entropy contribution can be very important. So now you can plot different energy terms, and and you can see but if you want to look at the energy terms, let's look at the I will make a simple so I have the reactant here, I have the transition state here, I have the product here. I will try to report the energies and find out the reaction barrier. Okay, so let's look at this is our NEB calculation. It has the transition state and the transition state. I will look at the final Gibbs free energy. So let's put the final Gibbs free energy of the transition state. So the unit here is Hartree, which is the common unit we use in computational chemistry or physics. So this is in Hartree or atomic units. And then let's look at the reactant. So I just want to look at the output file and make sure that it is optimized. So it is not fully optimized, unfortunately. Oh, okay. But why it does not? Oh, I see. That's too bad. I did not run the frequency calculation there. Okay, so I will quickly run the frequency. So I forgot to put the FREQ keyword here, so it didn't run the frequency. So I should do frequency separately. So it is going to be a quick calculation anyway. Sorry. So I will do the same for the product. Okay, so now I ran the frequency for the reactant, and let's look at the structure and make sure that it is this is the reactant and frequencies. It's a very fast calculation anyway. So, oh, it has an imaginary frequency. Ooh, it's too bad. So so that's not good. Okay, so we must re-optimize it with relatively tight convergence. How about the product? The product is good because all frequencies are, well, it looks like the reactant side. Okay, so I have the reactant and product exchanged somehow. Okay, so this is our reactant side, so it looks good. Now it is all positive frequencies, and then we can look into so if you look at the output file here, and you can find out the Gibbs free energy over here. So, and then now we can get the, if you subtract these two, oh, it's a very high energy barrier anyway. So I converted the value into a kilocalorie per mole. And then you can get a relatively large barrier, very high barrier, about 50 kilocalorie per mole. It looks like a very difficult reaction. So this is the free energy barrier. So this is the free energy barrier. So because we used the Gibbs free energy, and it has the entropy, so that's important. And let's try to get the potential energy barrier. If you want to get the potential energy barrier, we must not use thermal corrections. So and then in that case you want to find out the potential energy of your system, which is reported here. This is the electronic energy, and you can take the electronic energy here. This is the electronic energy of the reactant, and of course you must use 0 point energy. You can add the 0 point energy into that. Okay, so this is the total. And then let's look at the transition state. So now we are interested in the potential energy, so you can go and check the potential energy here, electronic energy. This is the potential, the electronic energy of the transition state, and we add the 0 point energy on that, and that would be our total. Now let's take the energy difference here. So now you can see the potential energy barrier is slightly lower, right? So this is the free energy barrier. It is slightly higher because it has entropy. And of course, the free energy contribution includes a 0 point energy, so you don't need to worry about it. And you can also, if you are interested in getting just potential energy without 0 point energy, you can drop this, and then the energy can be changed anyway. So you should add the 0 point energy in computing the potential energy barriers. So you can see a slightly difference between potential barrier and the free energy barrier. I haven't add the product energy here. You can do. You can try by yourself, and the idea is the same basically. So okay, let me summarize what I did. When you want to look at a reaction, when you want to calculate a reaction barrier, you start from the transition state. Okay, so first step is to locate the transition state, and transition state can be computed using NEB method. And to do that, you must use an approximate reactant structure, and you are going to make approximate product structure. That must be approximate, not perfect. And also you can use both reactant product together with the transition state if you want to run NEB calculation. So you have two options. And then you simply run the NEB calculation, and then after running the NEB calculation, you will get the transition state. So and you will find the imaginary frequency. You can always look at it and make sure that the vibrational motion showing for this imaginary frequency corresponds to the reaction you really study and you really want to compute. And then starting from the transition state structure, we ran IRC calculation, and then you can see the IRC path. So it has the transition state structure here, and approximate reactant and the product structures. So we further optimize starting from the final, the last point here to get the reactant, and the last point here to get the product. And then you can look at the energies. You can either use electronic energy plus 0 point energy to get the potential energy of the system, and then you can compute the potential energy barrier. And in some cases you may be interested in computing Gibbs free energy. So you can use the total Gibbs free energy to get the free energy barrier. My recommendation is to use the free energy if you have a bulky system, because in bulky systems entropy is very important, and it can affect the barrier a lot. And if your system is not really bulky like what we are doing here right now, the entropy effect may be very low, but still by looking at this number you can see so about 2 kilocalorie per mole different. Okay, so the potential energy barrier is about 2 kilocalorie per mole lower. So this is very important. Now I will give you a little bit more so how about so actually here you basically focused on a reaction like a single step, but some reactions may be multi-step reactions, right? Complicated potential energy surfaces. In such cases, again, you can step by step compute reaction barriers between different possible intermediates. For example, I will show you one of the example we investigated recently. So here you see, so this reaction is basically the reaction between acetaldehyde and hydrogen, and you can see it has so this reaction can give many different products, and then if you want to explore all possible reactions, you must compute the multi-steps. So here is the first step, reaction between hydrogen and acetaldehyde to give this radical, and then this radical can react with hydrogen to generate several products. So that is the realistic situation. And then these products can further react. So you see the potential energy surfaces or the free energy surfaces are not very simple. They can be very complicated because some reactions have more than one steps. So you can still compute them very carefully and get the reaction barriers of individual steps. Right, okay, so now let's see if you have questions. How sensitive is the IRC path to the level of theory? Can we trust a cheap IRC path? Probably not a good idea to use a cheap method to run IRC, because it's better to use a reliable method to get the transition state, and a reliable method, I mean the same methods to get reactant and product. We typically employ DFT. Omega B 97 XD is one of our favorite density functional, and F2 ZVP is one of our favorites, and we usually employ sophisticated methods to compute reaction paths. If you use cheaper method like smaller basis set and simple density functional, your accuracy may be not that good. Another question is here, are these calculations can indicate or distinguish between the cis and trans conformation of some molecules? Yeah, like the dangling OH4 ice molecules that can be linked either to other radicals. Yeah, it is a big question. Maybe we can start a discussion about this in Slack. Many questions. Are these calculations can indicate the cis and trans conformation of some molecules? Yes. You can compute these different conformations and you can compare the energy of different conformation. If a reaction goes to one conformation compared to the other, you can still compute the barrier for the reactions. Yeah, but yeah, I think what you're saying is right. Are the conformations have the same energy? I don't know. That's something you should compute and figure it out. Yeah, the isotope effect, maybe the isotope effect is there. You can do computations and figure it out. We have a tutorial. I'm going to talk about it shortly about computing kinetic isotope effects, and you can use that in your problem. And when does homolumo come into play to understand the reaction makes sense or not? Is there a way to describe these orbitals? This question is not really clear to me.
Hi.
Yeah, you can
I'm
ask
back
it.
again. So
Yes.
when I'm talking about the HOMO and LUMO orbitals, so how do we interpret like these orbitals in the context of a reaction? Like, what should we look for when looking at these orbitals in terms of reactivity? Does it make sense to look at them?
It's interpreting the reactivity based on orbital is a different approach, I would say, because it will not give you a reaction barrier. You cannot really get the reaction barrier detail, but probably I'm not really an expert to interpret the reactivity based on the molecular orbitals, but it can give you some idea about the selection rules. Probably you can see some orbitals, homolumo. If you have a reactant coming and homolumo can interact with the molecular orbitals of the reactant. So depending on the attractive or repulsion interactions, you can get an idea about the reactivity. So I'm not really an expert in analyzing MOS, but there are a lot of details in the literature. So the Hoffman's work and Fukui's work mainly focus on this topic. So
Thank you.
yeah, so I think you can have a look.
Because if not in quantitative energy terms, at least like visualizing the orbitals and which, if there is like overlapping orbitals that can occupy lower energy states or comparable energy states, maybe that could contribute to give like a qualitative description. One could do like both. Could do
Yeah.
like the energy term and then look at the orbital and say, look, this happens because there is a pi-pi interaction, or this orbital is interacting with that orbital. That could
Okay.
like give
Yeah.
a broader
Right.
description.
Yeah.
What
So
do you
what you're
think?
saying is now you computed the reaction barrier, then you want to understand why the reaction has a high barrier or low barrier, and you want to get more insights.
Yeah,
Yeah.
maybe.
Yeah. Okay.
Hopefully.
So in that case, you can look at the molecular orbitals, which is one way to do it. But there is another way to do it. I can find which is called the energy decomposition analysis. And so you can do energy decomposition analysis for so this is a different program, but anyway, so I will explain now how energy decomposition analysis can help you. So it can actually break down, let me find out the okay, so so let's say you have a reaction, and then and you want to understand reason for high energy barrier or low energy barrier. One way to look at the molecular orbital, it will give a very qualitative picture, but if you want to get a quantitative picture, you must do an energy decomposition analysis. In energy decomposition analysis, interaction between your two components at the transition state, you can decompose this interaction term into different energy terms, like electrostatic, polar repulsion, orbital interaction, dispersion, sometimes solvation effects. So and then you can look at what energy component is significant. For example, for some reaction, electrostatic interactions can be the dominant component for the high energy barrier. Sometimes it may be polar repulsions, maybe orbital interactions. So this is actually a very simple task if you want to compare. So I can share some of the literature in the Slack later, and you can have a look. So this is very very good actually. It can give you a quantitative description about the reason for the high energy barrier, low energy barrier, so you can get some insights. And then of course, if you want to modify the reaction to lower the barrier, you can really focus on the important components. For example, if the electrostatic is quite important for the higher barrier, so you can tune the electrostatic interactions by changing the molecular system, so something like that. So it's quite useful. So I will share some literature in Slack. You can have a look.
That's a good way to have another decompose, like quantification of the contributions to the state, and to probably to what's the major responsible, or the main responsibles for the for the transition, for the reaction to happen. I was asking about molecular orbitals because if you look at any output from Gaussian or Orca, you see like that there are many orbitals drawn when you take the output, and they're not very intuitive to interpret if you think about it.
Yes, you're right.
It's not something like, force field. It's just one giant ball next to an atom, and that's it. When it comes to like QM, the overlapping orbitals and the way they are drawn is not very intuitive. You can't really tell what the meaning of the actual HOMO and LUMO in the context of the molecule. It's, at least for me, it's very hard to decipher the drawings.
Yeah, that is true. In the recent years, most people focused on energy decomposition analysis rather than looking at the molecular orbitals, because it can give you very detailed picture. And personally, I like the energy decomposition analysis. In our tutorial, you can find I think they have an energy decomposition analysis, but I haven't really done it in OCA program. Yeah, they have the local energy decomposition. So you can get again. Yeah. So here you see they have, you can do some detailed analysis here as well. I haven't done this for my research problems. Again, you can see you can decompose the interaction between two components, and then you can decompose into different energy terms, and then you can get an idea about which energy term mainly contributes for this interaction. That interaction caused the reaction barrier anyway, so you can quantify it in a way. So the next step is to discuss a little bit about the kinetic isotope effects, because this is a very important topic. Okay, I cannot go into the full screen, unfortunately. Okay, sorry, I cannot go full screen, but I will try not to go in full screen. Maybe the PDF version will. Okay, the PDF version seems working. Okay. Now you have an idea about how to perform transition state computations, and then you can use this knowledge for some practical applications. For example, calculating kinetic isotope effects. In this case, we calculate the computation. We calculate the reactions with isotopes. For example, this is a very simple example where you can see methane molecule react with OH radical to form CH3 radical and water. And what would happen if we have deuterium instead of hydrogen here? And of course, this is a heavy element, and it affects the reaction rate. If you want to compute the kinetic isotope effects, the first step is to compute the transition state for this reaction. So you can use NEB computation, which is very easy to do. Okay, you can use the same approach we used in the morning. They are using this methods omega b 97 minus 3z so our idea is to get this ratio, right, constant of the hydrogen atom transfer and the deuterium atom transfer. So we want to get the free energy of the reaction barrier with the hydrogen here, and then we want to get the free energy barrier of the reaction with deuterium substituents. and then you can simply use this equation and get the kinetic isotope effect. So for the NEB calculation, you can create the reactant complex, and this is the product complex, and it's very easy to run NEB calculation using this. So if you go to ISE, and you can find kinetic isotope effects. Now here you can see approximate reactant, encounter reactant, and encounter product structures are there. You can use these two structures as a starting point to compute the NEB. Okay, that's essentially what we did in the morning. The input file is here. You can find this input file in the tutorial over here, and then you can simply get the transition state. So I have done this last night, and let me check my result. Here is the output file of the NEB computation, and this calculation may take a while depending on your computer speed, but it's not a big calculation anyway. You can do it very quickly, and then let's look at the outcome, and it's a normal termination, and I have the thermodynamic data, and let's look at the vibrational frequencies here. So so here you can see I have one imaginary frequency, a relatively large one, and also another smaller one. So it is not good. So we must we must repeat the computation anyway. So you can make the tight convergence. You remember in the vibrational analysis tutorial they mention about it. Is it here? Probably we can use tide optimization to avoid this problem. So, and we should use tide optimization, I think. But anyway, we don't have much time, so I recommend you to use this keyword in the input file if you encounter imaginary frequencies more than 2, so you can avoid the extra. Now after getting the transition states, you can simply so this is the NEB calculation, and then you get the transition state for the using using methane here and OH. So you get the NEB calculation done, and then you have transition state. So you have the transition state. So you get the transition state, and then you perform the IRC calculation to get the approximate product and the reactant, and then you can optimize it to get the reactant, and you get the product, and you have the transition state. So in this way you can get the barrier here. Okay, delta G. You know how to do it now. And the next thing is the potential energy surface is there, and we have the potential energy barrier or the free energy barrier. Now the next step is to replace hydrogen by deuterium. When you do that, we don't change the potential energy surface, we just change the 0 point energy. So we don't need to repeat all computations, NEB calculation again. You just replace hydrogen by deuterium and then perform the frequency calculation. That's enough. You can do it for the hydrogen, you can do it for the reactant, transition state, and the product. You simply run the frequencies calculation, okay? But you must change the mass of the hydrogen. You can simply put the isotope here, and then the Gaussian, Oka-Noss, you are working with the isotopes for these 4 atoms. So start from the optimized structure of the transition state, reactant or the product, and then simply replace these by the isotopes. So when you do that, so let me clean this mess. So then you can get the so this is the NEB transition state I computed. It has the electronic energy of minus 24.678 and blah blah blah, and then here is the 0 point energy. And when I did the frequencies by using isotopes, it is not going to affect for the electronic energy. It is the same, but the 0 point is going to change. So and of course it's going to affect for the free energy. And then here you can see the free energy, final Gibbs free energy for the NEB calculation. And when I run the frequency using isotopes, the free energy is different now. Okay, so and then you can do the same for the reactant and the product. When you do that, when you do that, you will be able to find the free energy barrier for the reaction with hydrogen or the deuterium, and then you can simply use this equation to get the kinetic isotope effects. You can essentially follow this tutorial and it explains everything. So So here it says the computed value is 7.17, which is in agreement with the experimental value. So which is nice. The agreement is very good, and I recommend you to try this by yourself. Let me check the questions. Okay, can we freeze the atoms while performing NEB calculation? Is it a good practice? Well, you can in principle freeze atoms during NEB calculation or optimizations, but it may be not good practice. But it can help sometimes, because if a transition state is very difficult to locate, you can simply freeze some atoms and optimize it, and then you can use that optimized structure and then maybe go to transition state calculations. And there are other methods to locate transition states. So if you can really guess the transition state, you can directly run transition state calculation as well. In that case, I will find out if you go into the manual and use OPTTS keyword, yeah, so if you know, if you can guess a proper transition state, you can simply run transition state optimization using this keyword. Okay, so it can give you the transition state directly, and then using that transition state you can go for IRC calculation. When you do that, it is important you run the Bayesian calculation at the beginning, and it will give you better force constants to initiate the computations. So this is another way to get transition states. So in this way you don't run any B calculations, so you directly run the transition state optimization. It's a different algorithm. It works really well, so I used it in some applications. Sometimes you can also get scans. You can also do some scans, and do they have a tutorial for that? I'm not sure actually. No. So this is about constraint optimization. So there was a question about freezing some bond distances, bond angles. You can simply freeze some bond lengths, bond angles, and optimize it. So you can simply freeze bond distances it says bond distances constraint, atom 0, atom 1. You can freeze angles, dihedral angles, and you can also study some simple potential energy surface through scans, and here it changes the atom 0 and 1 distance. This is hydrogen HF molecule potential energy surface. So it changes from 1 angstrom to 3 angstroms in 12 steps. Yeah, so I will share this in the chat box. Oh. Direct TS may give error. Well, it depends. Direct transition state computation may not give errors, but it depends on your starting point. If you can make a reliable guess, it's possible to use direct transition state optimization. If your guess is far away from the real transition state, it may not converge. Is there a way to guess the products? It is a little bit harder because in the NEB calculations we do now, or the transition state we do now, we really know what is the product. And then if you don't know the product outcome, I mean the reaction outcome, if you don't know, you can use some different techniques. There are some techniques which I can share in Slack. Some literature you can read. You showed a slide of a reaction on amorphous solid water. Okay. I have been working on similar problems, and I have a lot of difficulty to find transition state of these systems using. Oh, okay. Can you recommend a good DFT methods to finding? Okay. Such as hydrogen atom addition. Oh, okay. Well, you are using an excellent method, and my recommendation for you, if you use OCA, you can run NEB calculations. But my calculations in amorphous solid water, I used a different computational program, which is Gaussian 16, and they have different algorithms to get transition states. So in my experience, the Gaussian 16 maybe relatively easy for me to get transition states compared to OCA. I'm not saying OCA is bad, but it also depends on your experience, and if you have more, if you practice more and more, you can be you can get more information, and you can know more tricks. Why did you use OBT keyword for scan? Because we are going calculation sync. Okay, so the scan can be two types. It can be relaxed scan. This is a relaxed scan. It means you change the bond distance and optimize the structure at individual point. So that is a relaxed scan. If you do rigid scan, you don't use optimization here. So a relaxed scan would be more accurate. Again, depending on the problem you're working on. Well, that's true, but the optimization means okay. So when you do a relaxed scan, you freeze the bond distance. For example, let's say here, initially, let's say the HF. So you keep the two atoms, and the distance is about, let's say this is 3 angstrom, and then you freeze this distance. So and this is actually a very simple situation. We don't really want optimization in this case. In principle, it's simply 2 atoms, and it has no bond angles or the torsion angles to relax. It's just 2 atoms, so it doesn't really need optimization. But if you use 2 water molecules, for example, let's say you use 2 water molecules, and you try to scan the bond distance of 2 oxygens. Now the optimization is very important, because when they are apart, when they are closer, you don't really need well, you really have to have optimization, because depending on the distance, the shape of the molecule may be different. But in the HF case, you don't need to worry about. You can, I'm not really sure, I haven't done this job, but in principle we don't need OPT in this case, because it's simply 2 atoms, and OPT may be not required. Without OPT, the algorithm may work or may not work. I don't know, which you should try. So about this ice problem, probably we can discuss separately. You can email me the details, and then probably I can give you some guide. So you can email me the details. Do you have more questions? Anything on Slack? So if not, I think we should take a break now, and I will keep the Zoom open. You can keep posting your questions, and I will stop the recording.